Hi, I'm Sophie from Bayes Consulting, and once I'd agreed to take part in the great big internet math-off, the trickiest decision were the 3 topics to present. There are so many fantastic areas to talk about. If you don't believe me, just look at the presentations from all the other competitors. So what I've decided to do is talk to you about the 3 topics which are really close to my heart. The ones that have been at the centre of my studies and my career, the ones that make me smile and have been a huge part of my life. So, where better to start than at the very beginning, when I was 16 or 17, doing my A-levels in the Saunderson Science block of Penistone Grammar School, in the physics room, which was on the bottom floor, on the right-hand side as you walked in. Now, I don't need to close my eyes to still see that room. There were the big, heavy, wooden, square science tables in the middle, and at the front was a green chalkboard that moved around in a loop. And one hot day when the sun was coming in through the low windows, I remember being absolutely fascinated by what my science teacher, Mr. Brain, was drawing on the board. And what he was talking about was Bernoulli's equation, and it is that equation which got me fascinated by fluid mechanics, which was really handy because I absolutely loved aeroplanes as a teenager. What Mr. Brain was drawing was a pipe, and it was a pipe that had one width which went down into a narrower width in the middle and then went back up to a wider width at the end. And moving through that pipe was a fluid, and the fluid was moving nice and calmly. It didn't have any swirls, it wasn't turbulent, and the fluid also had constant density. Okay? Now, what happens is as that fluid started to move through and the width of the pipe decreased, the velocity in the pipe had to increase. Now, in best Blue Peter fashion, here's one I made earlier. If we think of each of these circles as showing how many marbles move through in any given time period, let's say a second, then when the pipe is really wide, we can get 12 marbles through in any second. If the pipe gets smaller, well, now we can only get 4 marbles through, but I need to get 12 through in every second, and the only way to do that is to increase the velocity. Decreasing the width of the tube increases the velocity and therefore the kinetic energy of the fluid. The increase is due to the work needed to push the fluid through the tube, and we mustn't forget that if the fluid changes vertical position, there'll be work done by the gravitational forces acting on it. Now, the change in pipe diameter also creates a pressure difference, and that too results in a force acting on the fluid. In fact, force is pressure times area, and we know that work's being done to increase the kinetic energy of the fluid. So, as the velocity of the fluid increases, the pressure decreases. How counterintuitive is that? What's even better is the fluid doesn't have to be in a pipe for this to happen. It's in any rapid moving fluid. Think of the annoying habit of your shower curtain bulging in. That happens because the rapidly moving water and air creates lower pressure inside the shower. And if you don't want to get wet when you see this effect, look at the paper tent being blown. Paper in our house tends to be blue to make the word stay still, but if I gently blow through the middle of it, you might think that the sides of the tent would puff out, but the rapid air of my breath decreases the pressure inside the tent, and actually the sides move in. An awesome experiment for Bernoulli's equation is the Bernoulli blower, which you can see here. So this is a Bernoulli blower in action. What it is a stream of fast air coming out from the blower, and in that fast air there's lower pressure than the air around it. That effectively creates a wall of high pressure that keeps the ball in place. It's quite mesmerising to watch. When you first put the ball into the air, it often bobs about up and down until it finds its equilibrium. That is when all the forces cancel out and it stays in place. At that point, if you're lucky, you can start to see the ball spin round, and that's something actually I could watch for hours and hours on end. The other thing you can do with the Bernoulli blower is when you've got the forces in equilibrium,
is you can start to tilt the actual Bernoulli blower, and the stream of air, as it moves, will take the ball with it. It's a brilliant example of maths in action.
So, there you have it. A brilliant equation which to me was completely counterintuitive, but explains why my shower curtains can be super annoying, but it's also used in sales, measuring velocity, and for fun tricks with paper.